I would like to thank the organizers for giving me this opportunity to speak. I would like to speak about some properties of the Specht polynomials. And so let me start with this page. Suppose R is a polynomial ring, and consider this linear map, which is a sum of differential operator. The kernel of this D is, as I said, the set of solutions of the linear partial differential equation, which is this. So yeah, this is a set of solutions of the linear partial differential equation. So the set should be a commutative ring. If you know it, it's easy to make computation to know the kernel. Because it is closed. It is a commutative ring because it is closed under plus and multiplication. Because we have this very good, very well-known equality. So it's only a matter of to know the generators for it. So it is clear that the ring of invariant, the set of solutions is this subring of the polynomial ring. And I'd say that any product of this kind of linear forms is a Specht polynomial. Next page. How can I go? Okay. So such a product can be expressed by using Young tableau, for example. Ivan. Okay. So T can be used to denote such a polynomial. Okay. I am particularly interested in the two-row square-free Specht polynomials. These are certainly finite in number. So let me speak about square-free monomial, square-free Specht polynomials. Let P be the vector space spanned by the square-free Specht polynomials. It is a finite dimensional vector space. So we may write it as P is the sum of these things. The subscript moves from K to K0 to one half of N. Because whenever there is a column with two boxes, there are two variables. And because I am interested in square-free polynomials, K can't exceed one half of N. Of course, I can use normal results. It is well known that Pk is spanned by the Specht polynomials defined by the standard Young tableau of shape lambda, two-row Young diagram, where T has a filling like that. This is the most general expression for such a polynomial. Integers in boxes are row-wise and column-wise increasing, and no repeats are allowed. And the dimension of Pk is certainly the difference of the binomial coefficients. For example, when N is 6, when there are 6 boxes, there are only 4 types of Young diagrams with 2 rows. And these differences are 1, 5, 9, 5. So P1 has 5 dimensional, and P2 is 9 dimensional, and P3 is then 5 dimensional. Next, I want to consider monomials. Suppose E is the vector space spanned by the square-free monomials. Then certainly it is closed under operations in these differential operators. It is because exponents are only decreases when these operations are applied. And D is a surjective map from R to R. But when it is restricted, it is not necessarily surjective. At an early stage, when the degrees are big, it's injective, and later stages, it is surjective. And the Hilbert function of E is certainly this sequence. It's a Hilbert series of a complete intersection. How do I go to the next page? Okay. So I like to use these notations. Suppose if it's an element of polynomial ring, then by writing a circle on it, on the right of it, I just simply means to change the variables into differential operators. That's my notation. And so, for example, if L is a linear form, L circle simply means this differential operator, which is sometimes called a polarization when coefficients are variables. And this is honestly, this is the same thing as Chris is talking about this morning, but some explanation I omit. And these notations are used in this way. D of F and D dot F and L circle F are all the same thing. When V is a graded vector space in R, V circle F denotes this set, which is, of course, a vector space. And when S is a subring of S, I also write S circle F, which is, of course, a finite dimensional vector space. Okay. I am thinking, I think everybody agrees that this S circle F is has a symmetric Hilbert series, I suppose. And for S, I am thinking of this. When I is like that, for S, I am thinking of this kind of sub-polynomial ring. How can I go to the next page? And let me let L be the sum of variables and En be the product variables. Both E1 and En are very important. They are invariants of the symmetric group. And when I say that sigma is a permutation, I am thinking of it as a 0-1 matrix, permutation matrix. When we are given a set of non-zero elements, then, and when sigma is a 0-1 matrix, I want to define sigma prime to be weighted 0, 1 matrix. 0 has been in the same position, but 1 has been replaced by this kind of quotient of the given variables, given constants. N prime is another set of matrices, but it is a symmetric group. The monomials En is not only an invariant of Sn, but it also is an invariant of Sn prime whenever these non-zero constants are given. Okay. I want to call that. I said P is the kernel of D when the weights are all 1, but I call it also a primitive space. It is spanned by the Specht polynomials. So Specht modules and primitive spaces are almost the same thing. And in the next 2 pages, I want to explain my situation. Please consider it as a subspace of a polynomial ring. But it is a space spanned by all the partials of one single element, which is now I call it En. And L circle is this differential operator. And kernel of L circle is P. And pk circle consists of minus k maps, degree minus k maps. This arrow denotes L circle. And okay. And in this diagram, red boxes are primitive spaces, kernel L circle, and the blue boxes are, I want to call like this. Blue boxes are, I want to call dual primitive spaces. And my problem is if prime is given in a red box, I want to find f in a blue box such that this equality holds. That's my problem. So first line, please read the first line. Given a prime, find f in pk star such that its image by L n minus 2k is f prime. Because this gives us a Jordan basis for L circle. L circle will have maximal Jordan type. So this is why I am interested in this problem. I have said about dual primitive spaces. For any fk, ft, Specht polynomial shape lambda, we have this very nice formula. Line. It is interesting because when ft is an element in a red box, and as soon as ft is given, we can compute this element. So it is an element in the blue box, and so this equality is a kind of answer to my problem. So, and actually, this equality can be generalized to a more general linear form. It is easy to see that this equality can be generalized to this weighted linear form. The kernel of this map is just minus this 2 by n matrix. It is enough to choose n consecutive, n minus 1 consecutive matrices enough. In this case, Specht polynomials have to be adapted in such a way that yes. Page 4, page 13, page 12. Yes. This formula can be generalized to a weighted linear form L. For this purpose, I have to define the new constant Vj, which is a kind of contragradient weight, like that. When this to be defined in this way, then we have this nice formula also. So I go to the next page. How can I do that? So my next problem is this. I want to extend this equality. What if can replace En in this nice formula? And this is interesting, at least for me, for 2 reasons. You can do it. I can do it. Circle F is another SL with a circle as an SL element. And secondly, probably I can find a subring bar, which is a CI. And so it has a Lifshitz property. So this is a reason why I am interested in this problem. I want to extend this equality. This is page 13, next one, page 14. Not only E1 and En are important, every K is important. Ek means the elementary symmetric polynomial of degree K. And let these things be a complete list of monomials in degree E1 to En of degree N. These are a basis for this. For this space, which might be called NRE enic, symmetric NRE enic. It's a specific symmetric NRE enic. And it is indexed by the Young diagrams. This dimension is a number of Young diagrams of N boxes. And suppose that if is one of these I went too far. Suppose f is one of these monomials. They satisfy this nice formula, but sometimes it is 0. And I have been unable to tell in which case it is 0. I don't know. But anyway, otherwise, they satisfy very good formula. Therefore, these led me to consider their linear combinations. Next page. Okay. So this is my conjecture and problem. Statement in the item 1, it says let F be a linear combination symmetric polynomials. So F is really an n-ic. Suppose R circle F has H vector, it has the same H vector as the CI. CI is a complete intersection. Then I suppose that this equality holds. And this constant is non-zero for most of the case, most of the time. But sometimes it might be zero. But in that case, even if it is zero, I think I can make a linear change of variables without destroying the symmetry. I think it is possible to make the constant non-zero. And in item 2, what it says is the difference between 1 and 2 are only the group. In this statement number 1, I was assuming that the group is a symmetric group. In this second statement, I am replacing the group by this Young subgroup. That's the only difference. And when the group has been replaced by a Young subgroup, still the same claim should be true. Item 3 is simply a problem. And Specht modules, primitive space, is a G module. Therefore, it is a module of a Young subgroup. And my problem says decompose it into an irreducible G module. I am not surprised if this has been known or written anywhere. But anyway, if the answer is known, it will help me. I'll go to the next page. 70. Nope. In the next 2 pages, I wrote something about, I made some remarks on Young subgroups, but I want to skip these 2 pages. So, yes. These considerations made me to define this family, F and F prime. F is a family of n-ic which has the same Hilbert function as a CI. And F prime is almost the same as F, but the Hilbert function for the space is at most the Hilbert function for a complete intersection, at most, or equal. That's the difference between F and F prime. So after all, I am trying to do this. This is a rephrase of my previous statement. When F is in F, then the AG algebra has the SLP, and the invariance is a complete intersection, and is SL with L as a reference element. I have not proved it, but I'm trying to do it. Yes. What is it again? Yes. At least K has to have characteristic 0. Yeah, I didn't say. Yeah. Can't I? I see. I see what you're saying, but you see,
to get a complete intersection, the characteristics of all the complex numbers, the group has to be generated by Python. And there's a complete list of groups.
no. In that case, the group has to be irreducible. The group has to be irreducible in the case. You can see. So no. I'm making two statements, and at least the first one has nothing to do with group, I suppose. Okay, yeah, that's nice. And I'll go to the next page. And I can show you some of the properties of it. My claim, I am conjecturing this. I have made a lot of computation, and I am thinking these things are true. If the family is an algebraic set, and it contains this algebraic set as a dense open subset, and if F is given, it will satisfy this equality, and it is not zero as a polynomial. And if it's closed under the action of the linear group, linear subgroup of the general linear group, I don't know how to call it, but I want to call it two-parameter subgroup, GAB. And it is closed, if it's closed under this kind of group action, and they don't destroy symmetry. So we have this inclusion. And let me go to the next page. F is an algebraic set. This is easy to see because it is defined by the algebraic relations of the coefficients. And it is three-dimensional as an affine set. This family F obviously contains all Macaulay dual generators for quadratic complete intersections. So let me explain these two parameters, P1 and P2. Mostly you can be assuming U1 and U2 are 1. And F contains a family of quadratic CI on which the symmetric group Sn acts, and F is no other thing than a single polynomial with parameters. I want to explain it. Recall that the quadratic complete intersection has a binomial sequence as the H vector. And consider this complete intersection, monomial complete intersection. The ideal generators are not unique. For example, their sum and the differences are also a basis for the same ring. There is no reason. Monomials are the best choice generators. So let me write their sum and differences. F0 prime is the sum of these monomials, And these are the differences. And differences decompose into linear factors. And without destroying the symmetry, I can replace F0 prime by this new symmetry. I just added this constant times E2. And I also multiplied this power sum by U2. And differences are going to be replaced by, I'm replacing only the second linear factor. It is replaced by this linear form. Because all the variables are treated, I haven't destroyed symmetry. And it's a it's just a permutation representation. And permutation representation is decomposed into two irreducible representation. One is an invariant, the other is another very easy standard representation. And I'll go to the next page, 20. And I can prove that in this space, these are only these exhaust all quadratic complete intersection with Sn action as a permutation representation. It was a surprise to me that this number 4, I mean, there are two parameters, actually, U1, U2, P1, P2, 4 parameters are involved. It was independent of the variable, number of variables. Note, this is a complete intersection. These generators, F0 to Fn-1, is a complete intersection in this idea, in this polynomial ring. So it should have the Macaulay dual generator for this single complete intersection. It has coefficients in this field. But clearing the denominators and homogenizing it, we have a uniquely determined polynomial, one single polynomial in this polynomial ring. So I have explained. I have changed a little bit about F and F prime and F double prime. First of all, if it's a family of any symmetric any, which is a complete section, and F prime consists of F such that our circle F has H vector the same as the Ci, and F double prime is a vector space which has H vector at most this binomial constant. So far, I haven't given you any theorem because almost all my claims are based on computation. But at least I have a rigorous place. This F double prime can be expressed by a single polynomial in the polynomial ring. This polynomial, but in fact, it is easy to see it is an element of this polynomial. So it is a polynomial. This polynomial will be, I want to denote this polynomial by F tilde, because it is a linear combination of these things with coefficients, this vector. And in the next page, I can show you an example. When n is 3, it looks like this. Yes. There are 3 polynomials, and the coefficients are like this. And when n is 4, I can show you this F in the next page. When n is 4, F is this complicated, but anyway, it is this. And these coefficients are certainly supposed to be not equal 0, because if they are 0, it will not be, it doesn't have same H vector as a Ci vector. I determine such a for n is 3, 4, 5, 6. The degree of D of the coefficients turn out to be like this. When n is 3, it's 2, and it is when n is 4, the degree is 4. When n is 5, degree is 5. When n is 6, the degree is 7. But I don't know what is D when n is 7. But anyway, this should be determined. So next, I want to consider how this group, two-parameter group, changes this polynomial, and it can be explained by 2 representations, phi1 and phi2. I'll go to the next page. First, I want to explain phi1. Recall that 0 is defined this way. It's anyway, it's anyway an invariant form. And I want to consider how this linear transformation, I don't know how GAB changes these parameters, these coefficients. By simple computation, I obtained these matrices, these elements. GAB changes this vector to this. And next, 29, so 20. Okay. Another one, which I call phi2, it can be explained like that. A natural basis for this space is those things. And if a general linear element is applied to these polynomials, it destroys the symmetry. But when G is in this group, it's a symmetric group, symmetric polynomial. So it is, it can be rewritten using the same monomials. So if you collect the coefficients, it gives you the matrix that explains phi2. This explains the action of the group to F. So I explained the action of the GAB to this family F. And phi2 is easy to handle because it is after a triangular matrix. According to my computation, we have this nice formula for this ft, no, f in this family. And the coefficient in this rectangle is, as a polynomial, it is, I guess, it is non-zero, but I don't know. I don't have a rigorous proof for it, but it's very natural to think it is non-zero as a polynomial. But if you specialize it to some certain value, then it could be zero. But even if this is zero, perhaps we can find some linear transformation of the variables without destroying the symmetry. I can make it coefficient non-zero. So I stop here. Thank you very much for listening.